Welcome to this session on inheritance and polymorphism. In our previous lecture, we explored advanced class relationships. We saw how classes can interact through friendship, association, aggregation, and composition. Now we take the next big step, that is understanding how classes can form hierarchies and share or extend their behavior. So this brings us to the powerful concepts of inheritance and polymorphism. So in this session, we will explore the following major topics step by step. We will begin understanding how one class can inherit properties and behaviors from another. We will see different types of inheritance, including single, multiple, multi-level, hierarchical, and hybrid inheritance. Then we will see access modifiers, that are public, protected, and private inheritance modes. Next, we will see function overriding, virtual functions, dynamic polymorphism, and finally we will cover abstract classes and pure virtual functions. So by the end of this session, you will not only understand these concepts conceptually, but also see how to implement them in C++ through step-by-step examples. Before we dive into code, let's remind ourselves that why inheritance exists. Inheritance models and is our relationship in which a derived class is a specialized form of a base class. So it gives us code reuse. Derived classes can reuse the base class data and behavior instead of repeating the code. Next, polymorphic design. Base class pointers can refer to the derived objects, enabling interchangeable behavior. And finally, a natural way to model hierarchies. For example, shape, circle, employee and manager, vehicle, maybe drive to car or a truck. So now let's explore the different types of inheritance in C++. The various ways one class can inherit from another. Inheritance allows us to represent real-world hierarchies and to reuse existing behavior instead of reinventing it. But depending on how many base classes and derived classes are involved, inheritance can take several forms. Each, you can say, is suited for a specific design need. So C++ supports five main types of inheritance. Single inheritance with one base class and one derived class, multiple inheritance with one derived and multiple bases, then multi-level inheritance, which is a chain of inheritance, hierarchical inheritance with one base and many derived classes, and finally hybrid inheritance, in which there is a combination of the above mentioned categories. Single inheritance is the simplest. One derived class extends a single base class, and it is used when you want a straightforward specialization. So you can see in this example, animal defines a common behavior, eat. Dog public animal, basically this line declares that dog inherits animal's public and protected members. In main, d.eat shows code reuse. Dog didn't need to re-implement eating. So you use single inheritance when there's a clear is-are relationship and no need to combine unrelated bases. Next is multiple inheritance. So multiple inheritance lets a class inherit from more than one base. So it is a powerful but can be more complex, especially when the bases share members, the diamond problem. So we will look into that problem soon in a moment. So you use multiple inheritance when a class truly is both of two different types. So here duck inherits behavior from both flyer and swimmer. D.flyer, D.swim show how multiple inheritance composes capabilities. So if both bases had a function with the same name and signature, then calls would be ambiguous unless this is disambiguated or solved with the help of virtual inheritance, which we will cover in a moment. Multi-level inheritance builds a chain, that is A is a parent class to B and B is a parent class to C. So each level extends the previous level. It is natural when you have a layered specialization. For example, sports car inherits method from both the ancestors. You use multi-level inheritance when you have progressively specialized concepts. Hierarchical inheritance means one base class has multiple derived classes. For example, shape is a parent class to circle, rectangle and triangle. So you can say that this models families of related types. All the drive types share some common behavior from the shape class, and this is great for polymorphic collections. So we will look into this when we will cover virtual functions later on. Finally, hybrid inheritance, also known as diamond inheritance, is a combination of more than one form, typically multiple and multi-level. For example, a bat is both a mammal and a winged animal. Both of these classes might inherit from a common base animal. So this forms a diamond shape hierarchy. Animal sits at the top, mammal and winged animal in the middle, and bat at the bottom. Without the virtual keyword, both mammal and winged animal would each have their own copy of the animal. Bat would then inherit two copies of animal, and this basically leads to ambiguity. So we use virtual inheritance to ensure that only one shared animal sub-object exists. So this solves the diamond problem in C++. So in short, hybrid inheritance combines the flexibility from multiple inheritance forms but must be used carefully to avoid any confusion. Now that we understand the different types of inheritance, let's dive into one of the most and sometimes confusing aspect of inheritance, that is access modifiers. Access modifiers define how and where the members of the base class can be accessed when inherited by a derived class. So they act as a visibility rules that protect the integrity of a class while still showing inheritance and reuse. So in C++ we have three main access modifiers: public, protected and private. Each of these determines how the base class members behave inside the derived class and outside of it. In this table we see the visibility levels clearly. So public members are open to everyone inside, that is inside the class, in derived classes and even outside. Protected members are accessible within the class and by the derived classes, but not by the outside world. Private members are strictly confined to the class that defines them, and they are completely hidden from the derived classes and external code. So understanding these access level is a key to designing secure and maintainable class hierarchies. In this example, we have a simple class base. Inside the class, we have defined three data members, each with a different access specifier. So public underscore var declared under the public section, then private variable declared under the private section, and finally protected underscore var declared under the protected section. The constructor initializes all three of them with simple values that are 1, 2 and 3. Now look at the member function called member underscore function. So this function prints out all three variables. Inside the class there are no access restrictions among its own members. A class member function has a complete access to all of its data, whether the data is public, private or protected. When we call member underscore function on an object of a class base, the output would be that is 1, 2 and 3. This confirms that a member function can access all the members of its own class regardless of their access level. Now that we have seen how access works within the same class, let's take the next step and see what happens when one class inherits from the other. So in C++, when a class, derived class, inherits from a base class, it doesn't automatically gain access to everything in the base class. The access specifier public, private and protected determine what can and what cannot be accessed from the derived class. So in this example, the class derived inherits publicly from the class base. Inside the derived class, we have a member function, member underscore function, that tries to access these three members of the base class. Now let's analyze what happens here step by step. So the first line in member underscore function prints public underscore var. So this is allowed because public members of the base class remains public in the derived class as long as inheritance is public. The next line tries to print private underscore var. So notice here that this is not allowed because private members of the base class are not accessible in any derived class. regardless of the inheritance type. So these are completely hidden from the outside access, even from the subclasses. The last line prints protected underscore vr. So this is allowed because protected members of the base class are accessible in derived classes. However, they are not accessible to the objects of the derived class from the outside. We have now seen how access modifiers behave inside the class and how they work inside a derived class. So the final question is, what happens when we try to access class members from the outside, such as from the, for example, the main function. So in real programs, main represent the external user of the class. That is a code that creates your objects and interacts with them. The access that main function gets depends entirely on the public interface that the class exposes. Let's walk through this code carefully. So in the main function, we have created two objects, one of the base and second of the derived class. Then we are trying to access three members, these three variables, from both the objects. So let's look into this step by step again. So accessing public underscore vr works perfectly fine. So the statement cout b dot public underscore vr is valid because this public variable is publicly accessible from anywhere, even outside the class, that is even from main. So this is valid, and the same applies for the subsequent statement, that is cout d dot public underscore vr, because public member of the base class remains public in the derived class under public inheritance. Next, see what happens when we try to access the private variable. So this will cause a compiler error because private members are completely hidden from the outside world. They can only be accessed from inside the class itself, not main, or not even the derived class can directly touch them. Next, see what happens when we try to access protected variable. So this also results in a compiler error. Even though protected variable was accessible in the derived class, but from the outside, a protected member is not visible. So as the main function is then outside function, so when the main tries to access protected variables using both b and d objects with cout statement, both will fail to compile. Now let's look into polymorphism and related concepts like function overriding, virtual functions, abstract classes, and interfaces. In object-oriented programming, one of the most powerful concepts is function overriding. So it allows a derived class to provide its own implementation of the function that already exists in the base class. So the key idea is that both functions, that is the one in the base class and the one in the derived class, have the same name, same return type, and the same parameter list. When that happens, the derived class version of the function overrides the base class version. So function overriding enables us to perform runtime polymorphism, allowing different behaviors depending upon the object type that is used. Now let's see why do we need it. So imagine you are designing a program for different kinds of shapes that may include circles, rectangles, or triangles. You want each to calculate its area in its own way. So instead of writing separate functions with different names, like maybe calculate area of circle, calculate area of rectangle, calculate area of triangle, we can define a common interface in the base class, maybe calculate area function, and let each derived class override it with its own specialized logic. So this gives us a cleaner, more readable, and more scalable code. Here the base class defines a function display, the derived class defines another function display, same name, same parameters, so it overrides the base class version. When we call b.display, the compiler calls the base class version. When we call d.display, it calls the derived version because the compiler know that d is an object of derived class. So this is compile time decision since we are calling functions directly using objects. So now let's see what is difference between static and runtime polymorphism. So polymorphism means many forms. So it allows the same function or operator to behave differently depending upon the context. So we have two main categories of polymorphism, that is static polymorphism that is resolved at the compile time. For example, function overloading and operator overloading that we have just completed in the last session. Then dynamic polymorphism, it is resolved at the runtime and it is implemented using virtual functions. So let's stop here and see the difference between static and dynamic polymorphism. So imagine we have a base class shape and several derived classes like circle, rectangle and triangle, and we want to create a list of shapes, and for each one we intend to call a function like area to compute its area. So we don't know at compile time, let's suppose, that which specific kind of shape each element in the list will be. If we relied only on static polymorphism that we have just seen, we would have to write separate functions or use complex conditional statements like a giant if or a switch to check each shape type. That would make our code rigid, repetitive, and hard to extend when any new shape is to be added. So this is exactly the motivation for dynamic polymorphism. That is basically a mechanism that lets us write a single interface that can call appropriate derived behavior at runtime. In other words, dynamic polymorphism gives us runtime flexibility. It allows a pointer or a reference to a base class to automatically call the correct derived function, even when the program doesn't know the actual type until the execution time. So let's look at the example of each. Number one is function overloading. So function overloading means multiple functions with the same name but different parameters, types or count. So the compiler decides which function to call based on arguments. So this is also called compile time polymorphism. Now let's go through this code stepwise. So the first function accepts an integer and it is used when argument is int. Second function accepts decimal or double type number. So it is used when your argument is of type double. And the third function takes string. So this represents textual data. For example, if we write hello or print hello, so this will launch this third function. So in the main function, when we write the three print statements, at each statement the compiler analyzes the argument type. For example, first the compiler checks that 5 is an integer, so it calls the relevant print function with integer as an argument, and so on. So it is important to recall that compiler decides which function to call before the program runs or executes. So this is called static binding, early binding, or compile time polymorphism. Next is operator overloading. That means giving special meaning to the operators for user defined types. So the concept is that you define a user defined data type. Then for example, the constructor initializes objects automatically. So let's move on to that operator function. So this function overloads plus operator. So in the main function, when we write point c is equals to a plus b, so the compiler converts this to a statement like that a plus b statement to a dot operator plus, for example. That is, it calls the overloaded operator function. So execution inside operator runs and new object is created and print message is displayed. So let's see why this is static, because the compiler again decides at the compile time which print to call, which operator to call. So this is not runtime. So if we want a one interface, many behavior and decisions to be made at runtime instead of compile time, then we move to dynamic polymorphism concept. So in this code we have a base class B and a derived class D. So in the main function we create a base class pointer ptr and we create an object to derived class named dv1. Then we assign the address of dv1 to ptr. So now the base class pointer points to the derived object. Now when we call ptr of f, what do you expect? Intuitively you might expect that since ptr points to derived objects, so the derived version of f would be called, the function f would be called. But when you run this program, the output is base class function called. That is surprising, right? So the pointer points to a derived object, yet the base version of the function is invoked. So let's see the reason why this happened. So the reason lies in the concept that how the compiler binds the function calls. At the compile time, the compiler sees that ptr is the pointer of type b static, so it assumes that you want to call the version of function f that belongs to the class b. So this is static binding or early binding. That is, the function call is linked to the base version at the compile time, because the compiler only looks at the pointer type, not on the type of object. In other words, the invoked function depends entirely on the type of the handler, that is the pointer or a reference, not on the type of the object it points to. So how do we fix this? We want the function that is called to depend on the actual object in memory, not just the pointer type. So that is where virtual functions come in. When a function in a base class is declared as virtual, the compiler sets up a mechanism called vtable or a virtual table, allowing the program to determine at runtime which version of the function to call, that is either the base one or the derived one. So this is basically an essence of dynamic binding or a runtime polymorphism. So to summarize, dynamic polymorphism C++ only works through pointers and references. Number one, when you call a function through a base pointer or a base reference, C++ checks if the function is declared as virtual. Then, if it is, the actual object type decides which function to call. That is basically dynamic polymorphism, because we are considering the actual object type. If you are not writing virtual keyword, that is, if the function is not declared as virtual, then the pointer type decides which function to call, and then that becomes static binding that we have just gone through. Now that we have seen what happens without virtual, we are ready to understand how virtual functions will solve this limitation. So a virtual function is a member function in the base class that you can override in the derived class. When you call that function through a base class pointer or a reference, C++ decides at runtime which version of the function to call, based entirely on the actual type of the object being pointed to. So this process is called dynamic dispatch or a dynamic polymorphism or runtime polymorphism. Let's walk through this code line by line. So in class B, we have declared the function f as virtual. This basically tells the compiler, do not decide at compile time which version of this function to call. Defer the decision until the runtime or execution time. Then the derived class D overrides this function with its own version of f function. In the main function, we create a base class pointer ptr and make it point to the derived class object db1. Now, when we call function f through ptr, the compiler sees that the function is virtual. So, as instructed, it defers the decision until the runtime, when it knows that the ptr actually points to a derived object. So the program then calls a derived version of f, and so the output now becomes in derived. So this message will be printed. So internally, when a class contains virtual functions, the compiler binds a hidden structure which is called vtable. Vtable is basically a table of function pointers that point to the correct version of each virtual function. So each object of that class stores a hidden pointer known as vptr, which points to the vtable for its class type. So when you call function f through ptr, the program actually looks up the function address in the vtable of the object being pointed to. If the pointer points to a base object, it uses base vtable and calls base class version of function f. And if it points to derived object, it uses derived vtable and calls the function of the derived class, function f version of the derived class. Here we show two methods, speak underscore non-virtual, which is an ordinary function, and speak underscore virtual, that is marked specifically as a virtual function. So the derived class doc defines methods with the same name. When a method is virtual, we say the derived method overrides the base one. Also note that the virtual destructor in the base. This is critical when you delete derived object through base class pointer to ensure proper cleanup. We create a dog but store it in an animal pointer. Then calling speak underscore non-virtual through a pointer uses a base class version because it was bound at the compile time, because we haven't used any virtual keyword with it. Then calling speak underscore virtual, this dispatches at runtime. This defers the decision at runtime. This calls the dogs overridden function because speak underscore virtual is specifically marked as virtual function. So this is how polymorphism lets a single interface, that is in this case animal class, represent many concrete behaviors, for example dog, cat and any other animal. So if a base class destructor is not virtual, deleting a derived object with the help of base pointer will not call the derived destructor. This causes resource leaks. So make base destructors virtual if the class is meant to be used polymorphically. Now that we understand both static and dynamic binding, let's step back and compare them. When each one should be used and what trade-offs come with them. So remember one thing, that static binding happens at the compile time and dynamic binding happens at the runtime. Each has its strengths and limitations depending on the situation. So static binding gives us speed and simplicity, while dynamic binding gives us flexibility and scalability. So the key is to choose wisely based on your design goal. If performance and predictability is critical, then you use static binding. If adaptability and maintainability is more important, then you should go with the decision of dynamic binding with virtual functions. So most of the real world applications combine both, that is static binding for internal operations and dynamic binding for interface driven behaviors. Now let's imagine you are building a drawing application. You know your app will support circles, rectangles, maybe triangles later. But here is the problem, every shape must be able to draw itself. Now ask yourself, how do I force every shape to implement a draw function? That's basically where a pure virtual function and abstract classes enter the story. Pure virtual function is a special kind of virtual function that has no definition in the base class. So it only provides a declaration of a function at the base class level, and pure virtual function is specified by placing equals to 0 sign in its declaration. Like you can see in this class, we have declared one pure virtual function named getVolume. Let's say we create a base class shape and imagine it has a draw function, but wait, does a generic shape really know how to draw itself? So the answer is no. Shape could be a circle, shape could be a rectangle, so each one draws differently. So giving a default implementation doesn't make sense. We do not want a meaningless default version or someone forgetting to implement draw function. So what do? We tell C++, I do not want to define this function here, but I want all derived classes to define it. So this is done or ensured using that equals to 0 sign, that is with the help of pure virtual function. So you can see in this example a shape class and we have defined a pure virtual function named draw. So virtual means to ensure that it enables runtime polymorphism. Equals to 0 signs makes it a pure virtual function. So now shape becomes an abstract class. So abstract class is a class that contains at least one pure virtual function. And there are some important rules. You cannot create object of a abstract class. You can create pointer or reference to it. And it must be inherited, and derived classes must implement a pure virtual function. So these are some rules associated with your abstract class. Now we create real shapes. So a circle class inherits from shape and it draws according to its behavior. Notice something important, if we forget to implement draw inside a circle, then the compiler will throw an error because we promised to implement it. That's the power of pure virtual functions. Now look at the main function. If we try to create a shape object S, so as this is a abstract class, so we cannot create an instance of it. We can only create pointers or reference to it. So this will throw an error. Next we create S1 pointer to a shape class. We are saying I don't care which shape it is, treat it as a shape. This is called upcasting. Now here's the magic. Even though the pointer type is shape static, that is of shape, the function called is of circle. That is, the draw function will be the version that is placed in the circle class. That is because of virtual function. So this is called runtime polymorphism, late binding. That is, the decision depends at the runtime. Now let's see what is interface in C++. So imagine again you are building a powerful graphics engine, for example. So you know one thing for sure, that every shape in your system must draw itself, calculate its area. But here's a twist: you do not know yet what shapes will exist in future. That is maybe circle, rectangle, triangle, or maybe even hexagon someday. So how do you design something flexible? That is where the interfaces in C++ comes in. So the core idea is that an interface defines what must be done, but not how it should be done. Think of it like a contract. So it says if you want to be a shape, you must know how to draw and calculate area, but it doesn't tell you how to implement those functions. So here's an example. Let's break this down stepwise and discuss. So we have a shape, we have a class named iShape with some pure virtual functions and a destructor. So equals to 0 sign basically makes them pure virtual function. That means no implementation here. Derived classes must implement them, and this makes iShape as an abstract class. Then virtual destructor. So why virtual? Because when deleting objects using base class pointer like delete s1, we want the correct derived destructor to be run. So this is good practice in polymorphic base classes. Next we have a derived class circle that basically inherits from the iShape class. The constructor initializes radius. So if we write circle C 5.0, then this will put the radius as 5.0. Now notice this is the draw function. So this is circle's own version of drawing. So again the area function, the formula used is pi r square. So the circle calculates its area accordingly. Then we have a rectangle class with its constructor, parameterized constructor, the draw function, overridden draw function, and overridden area function. Now a rectangle area is calculated with a different formula, that is width into height. So it is accordingly specialized behavior embedded into the draw function or in the area calculation function of the rectangle class. Now let's see the magic. So in the main function we have created two pointers, s1 pointing to referring to a circle class, and s2 for rectangle. So we are using a base class pointer. So again this is called upcasting. We treat circle and rectangle as a generic iShape. Now when we write a statement like call of draw function using s1 pointer, so even though the pointer type is iShape, at runtime it is decided to call the draw function of a circle class. So it prints a message drawing a circle. So this is runtime polymorphism. So even though both the pointers are of iShape, different functions are executed because of virtual functions, the vtable mechanisms, and the runtime polymorphism. So the big concept is interface, that is a common behavior, that is all shapes can draw, all shapes can calculate area, but internally circle uses pi r square and rectangle uses width into height formula. So same interface but different implementations. So think it of as a remote control. Every device must implement power on, power off, but how TV powers on is different from the air conditioner maybe. So remote defines what must exist, but the device decides how it works. So that is exactly what interfaces do. So this enforces consistency, make the system scalable, and it allows adding new shapes very easily. Now let's discuss another important concept, that is virtual inheritance. And the diamond problem that we slightly briefly discussed at the start of this session. So imagine you are building a class hierarchy. You start with a simple, you create a base class, maybe class A. So far everything is fine. Now you create two classes, class B and class C, inherited directly from class A. So both B and C inherit from A. Still okay. But then you create a class D, like D inheriting from B and C. So the chaos begins. So let's visualize this inheritance structure. So this creates a diamond. So this is called a diamond problem. Let's see why. Because D gets two copies of A, one through class B and one through class C. So inside the class D, in the class D you have a show function that basically prints a value. So when you create an object of D and then write obj.show, so the compiler gets confused. It asks you which value, either it is a B's copy of A or class C's copy of A, because D contains both, as it is inheriting from the both of these classes. So internally memory looks like having D having both the versions, so compiler can get confused. It sees two separate A objects, so that's why it is ambiguous. As a temporary fix, you could write a scope resolution operator, that is C or B of value or C of value, but that doesn't solve the real problem. You still have duplicate A objects. So the real solution is virtual inheritance. Now let's rewrite the B and C like this. So while inheriting, you insert a keyword virtual. So class B colon virtual public A, again class C colon virtual public A. So that single word virtual changes everything. It tells the compiler if multiple classes inherit from A, share one common instance of A. So now memory structure becomes easy to comprehend. Internally D has only one A shared instance. Now let's revisit the example. We have created B and C virtually. So even though both inherit A, they do not create separate A objects. Now the value variable is not ambiguous, and if you see inside the class D, because there is only one A associated with D. So the constructor order is very important concept. When you create an object D obj, number one, the virtual base A class A is constructed first. A constructed message is printed, then B constructor runs and B constructed message get displayed, and then C constructor runs and C constructed message is displayed, and finally the D constructor runs and D constructed message is displayed on the screen. So why is A constructed first? Because virtual base classes are constructed by the most derived class. Even though B and C inherit A, they do not control its construction anymore. So D is responsible. So that's it. In the next section, we will explore file handling and templates.